So, today we're going to start on chapter 7. Or did you have more questions from the homework before we do? Okay. Like I said before, this is a course that builds on everything that's come before. Today we're going to start talking about confidence intervals and sample size. You've no doubt seen statistics reported where it says 74% of students' stress comes from schoolwork. Or that of the students surveyed, that the certain percentage said that this was the source of their stress or whatever. And then they talk about with the poll has a margin of error of plus or minus 3%. Well, it's that plus or minus 3% that we're going to look at today. We're going to start talking about how do you quantify the error associated with that kind of a statistical analysis, with that kind of a result. Because that is, if you'll recall, one of the principal objectives of studying statistics is not just descriptive, but inferential. To be able to make estimates about populations from the statistics that describe them, from the samples. Specifically, you want to be able to estimate the value of a parameter of a population based on the statistics from the samples you get from that population. We've already seen, in fact, the very definition of sample error is a declaration that you're never going to get a sample that gives you the right answer. That's why we're not saying that this estimate is a measure of the population. The parameter is a measure of the population. The mean, the mu, is the parameter mean. The mean is a measure of the average, mathematical average of the entire population. Unfortunately, oftentimes that population is just too big to actually measure that parameter. So you measure the statistics of a bunch of samples of that population. And those statistics become an estimate of the parameter that you're interested in knowing something about. Okay? And I want to stress this one more time because we've talked in the past, recently. We did probability distributions and talked about the probabilities of getting 3 queens and 2 jacks, and those are perfectly legitimate calculations and things, perfectly legitimate uses of statistics and mathematics. But I want to make sure you understand that no amount of mathematics will ever make you a fortune teller. Okay, this, I laugh when I see the reruns of the old show about, I think it was called Numbers, where they used the 3 for the backwards E in the word numbers, where, the mathematician would go and tell the FBI, oh, look, if you do this analysis of the spray pattern of the water droplets, then we know that the kidnapper must be at this address on the 3rd floor in the 2nd room from the left. What? That's not how mathematics works. Okay? It don't. When you make an inference, when you make an estimate of a parameter, you're going to make an estimate of that parameter. Okay? That's it. We can talk about estimating the mean of a population, and the best estimate of a mean of a population is the mean of a sample. Now, but we already know that the sample mean is not going to be right. But it doesn't mean, you'll notice I didn't say that it's going to be an accurate prediction. I said it's going to be the best estimate. Okay? What does that mean? That means, well, if you try estimating the population mean by using the median or the mode or the mid-range, then you're going to get your answer is going to be even more wrong. It's going to be further from true. The closest estimate you're going to get, the best estimate, is the sample mean. And in point of fact, that would be called a point value estimate, or a point estimate, where you say, roughly speaking, what's the mean of this population? Well, let's take a sample, measure the mean of the sample. That's our best guess. That's the best estimate we can offer of the population mean. Oh, by the way, I promise you it's not right. But it's as close as we're going to get. That's the problem, and that's the reason statisticians don't like point estimates. There's no way to quantify how close is it. I don't know. It's somewhere between a little wrong and a lot wrong. I don't know. It's a point number. It's one number. What is the average of a single number? Meaningless. It's what it is. So how would we address that mathematically? What we would do is we would look for an interval estimate. Because when we estimate an interval, now we can quantify a level of confidence. So what is an interval estimate? Here's the example they give in the book. Our best estimate suggests that 21.9 is less than the population mean, which is less than 22.7. Okay, well, what's the midpoint of 21.9 and 22.7? Plus or minus is that right? 22.3 plus 0.4 is 22.7. 22.3 minus 0.4 is 21.9. So we would say our best estimate of mu, of the population mean, is 22.3 plus or minus 0.4. And to that, we could assign a confidence interval of, say, 90%, 95%. How do we assign? How do we quantify that confidence level, that uncertainty? Now, for the record, this is the estimate this is the interval. Actually, that's the interval. So what is the confidence interval here? No, it's plus or minus 0.8. So we have a confidence interval of 0.8 out of 22.3. But how confident are we that the actual mean of the population is in that interval? Excuse me for 1 minute. I'll be right back. All right. When we say this is our confidence interval, when we say this is our estimate with an interval, we're saying that with some measure of confidence, within some percentage of confidence, we believe that the actual value of mu is somewhere in this interval. The actual value of the population mean is somewhere in that interval. It might or might not be. But we can talk about the probability that it is by invoking the central limit theorem from last chapter. How do we do that? Well, we don't just take one sample. We take a bunch of samples. And those samples start giving us those samples, as the number of samples get larger, those samples are going to start to form a distribution. And the central limit theorem says that, in this case, the mean of the population, since that's the statistic we're looking at, will start to approach the mean of the mean of this distribution of sample means will start to approach the mean of the population. Now, we say that we have a 95% confidence. We are 95% confident that the mean of the population is within that interval. We're saying then that there is a 5% probability that it is not. And okay, I want to touch on this because it is important for you to understand what we're doing. This whole section, if you'll look at the title, is confidence intervals for the mean when sigma is known, when the standard deviation is known. Okay? Let me ask you a question. How do you know the standard deviation if you don't know the mean? calculate the standard deviation, don't you? Okay, well, I'm not going to say that it will never happen, that you won't be given a problem and said, this is the mean, this is the standard deviation of the general population, of the total population. Now estimate the mean. Okay. But I'm going to tell you that it's, for my money, this is the equivalent of, in a physics class, when we talk about, free body motion with frictionless systems, where we say we're going to assume that we're pushing this box across a floor that has no friction. Or we're going to assume that the pulleys are massless and the string is massless. Okay, it doesn't actually happen that way. But it is a convenient contrivance for studying and understanding the physics that are actually involved. And then, in this case, it's probably never going to happen that you're going to have a situation where you know the standard deviation of a population, but you have no idea what the mean is. Okay? But by taking this, by taking it from by taking this approach, we can look at the mechanics, the mathematics of exactly what it is we're looking at and studying, and how this works. And in the next chapter, we're going to expand and say, now, what do we do if we don't already know the standard deviation? Okay, because that's generally going to be the case. But from the central limit theorem, we know that mu according to the central limit theorem, if the sample size is large, about 95% of the sample means of same size samples will fall within plus or minus 1.96 standard errors or standard deviations of the population mean. Remember that? We start taking lots of samples of the standard deviation, and lots of samples from this population, and calculating the means of all those samples. Then, as n gets bigger and bigger, as the number of samples we take gets bigger and bigger, then 95% of them are going to be within that 1.96, that interval of 1.96 standard deviations. Now that means that if we take any one specific sample mean, x bar, there is a 95% probability that it's going to be within that interval. Because 95% of all of them are in that interval. Does that make sense? Here is your standard normal distribution. There's z equals 0. The mean of that distribution. You know what? back up a minute. We're going to say this is the population. And that's the mean of the population. Now, if we start taking samples, if we take any one specific sample, this is minus 1, that's, make that a little more clear, minus 1 sigma. 1.96 sigma is about right here. Plus or minus 1.96 sigma. We know that 95% of all of the means that the sample means that we measure are going to fall within this range. So for any one sample that we collect, there is a 95% probability that it will fall somewhere in this range. There is a 2.5% probability it'll be over in this tail, and a 2.5% probability that it'll be over here. 95% probability that it'll be here. Because it's within that 1.96. Now, we're going to look at where we get that 1.96, which goes back to the question you were asking from the homework, how to use that table E with the z-scores, okay? But look here at this blue rectangle that on page 364. Saying that x bar minus z over alpha divided by 2 times sigma over the square root of n is less than mu, is less than the sample mean plus z sub alpha over 2 times sigma over the square root of n. Now, you'll also see it says for a 90% interval, z alpha over 2 is 1.65. For a 95% confidence interval, z of alpha over 2 is 1.96. And for a confidence interval of 99%, z of alpha is 2.58. Okay, let me point out a couple of things here. You'll remember this started off with us saying, giving an interval of our estimate of mu is 22.3 plus or minus 0.4? Plus or minus 0.4. We're 95% confident that that's it. That's true. Well, why would we choose 95% confident and not 99% confident? Well, there's always some finite margin of error, but the point is we can make that interval. We can choose whatever confidence level we want. And again, just to make sure we're clear on our vernacular. This 95% is our confidence level. This plus or minus 0.4 is our confidence interval. We can choose any confidence level that we want. Why do we why would we not go ahead and choose a 99% confidence interval? Look back at the distribution here. This is our 95% interval. If we wanted to make it 99% confident, then we have to come out to here. And make a much wider, make a larger interval. We're more confident, but now we're no longer being as precise. So we're sacrificing we're sacrificing interval for level. Okay, if we want to make it just 90% confident, well then we could come down to here. A much smaller interval and still be 90% confident. Which means we now have a much smaller interval, but now we're 10%. There's a 10% probability that we're wrong. With this interval, there's a 5% probability that we're wrong. Even with this interval, there's still a 1% probability that we're wrong. Now, that is how this works. And it's all based on that standard normal distribution. Now, I got to point out a couple of things to you. All of this is based on a couple of assumptions. And the first assumption is that this population is in fact normally distributed. Okay? What if it's not? Well, the other assumption is that the sample size is at least 30. I don't know why they came up with that number, but they did. The book says 30. Okay? The two assumptions are that the sample is a random sample. That's one of the assumptions. That you've chosen this sample completely without any prediction or discrimination, or completely indiscriminate. And for reasons that I've gone over before, I bristle at using the word random. But you know what we mean, what the book means when it says random. It means that, never mind. That's the first assumption. The second assumption is that either the population is normally distributed or the sample size is at least 30. Now, the last thing I want to point out to you is this notion of the z of alpha over 2. Okay. What does that mean? Okay, well, if your alpha is your confidence interval, okay. I don't know why they don't just flat out say it. They tell you in there that it's 1 minus alpha is the relationship between confidence interval or a confidence level and alpha. The alpha is what's left over after the confidence. It's the probability that you're wrong. Okay. it is the complement of the probability that you're right. Okay? Here is what we're saying. We're talking about a 95% confidence interval here. Okay? This is the probability that we're right, that our estimate is right. This and this is the probability that our estimate is wrong. If this is 95%, then all of this plus all of this equals 5%. Okay. Or our confidence level. Now, why alpha over 2? Because there are 2 wings. So, here, this side is alpha over 2, and this side is alpha over 2. So in the case of the 95% interval, alpha over 2 to the left is 2.5%, or 0.025. Alpha over 2 to the right is the other 0.025. If we go to a 99%, alpha over 2 is 0.005 and 0.005 over here. If we go to a 90% interval, then alpha over 2 here is 0.05, and alpha over here is 0.05. Alpha over 2 is half the complement of your confidence level, not interval level. Now, let's look at this. Where's that? Let's look at this. Get out your table E. Now let's look at what I'm talking about when I said we're looking for alpha over 2 for a 95% confidence level. Well, that means the alpha, if we're looking for a 95% confidence level, alpha would have to be 5%. And 5% divided by 2 would be 0.025. Where do we find that? If you look at this chart, .0250 right there. What does that give us? Minus 1.96. And if that is our alpha over 2 here is minus 1.96, then plus 1.96 and above is the other 2.5%. Because the standard normal distribution is perfectly symmetrical. What if we wanted a confidence interval of 99%? Then our alpha would be 0.01 and our alpha over 2 would be 0.005. look here, we're going to have to choose between 0.0051 and 0.0049. Which one would we choose? Look on table E. See where I'm pointing? Here's the top. See, you've got 0.0051 and 0.0049. So which of those intervals would we choose? You want to be conservative. Exactly. That means that you're actually just a hair over 99% confident. But better to be a hair over if you're specifying 99%. And it's better to be just a hair more than 99% than a hair less than 99%. Okay. Well, look at what is the Z value for a 99%? Find your 0.0049. Now go up to find your column and over to find your row. Is this thing still following me? Maybe not. Okay. Here is our 0.0049. So it's going to be minus 2.58. Minus 2.58 would be Z of alpha over 2 for a 99% confidence interval. And where did they give us? They gave us these numbers right there. Right there in that middle paragraph. It says the value used for 95% confidence interval, 1.96, is obtained from table E in Appendix A. For a 99% confidence interval, the value 2.58 is used instead of 1.96. It also says that, well, it doesn't say here. Jordan, hey. But if we were looking for the 90% confidence level, what would alpha be? If we're looking for 90% confidence, then alpha is 0.1, and alpha over 2 then becomes 0.005. I'm sorry, not 0.005, but just 0.05, which would be right here in the middle. We would have to choose between 0.0505 and 0.0495. And again, we're going to be conservative and go with the smaller of those two. And that means our interval, our number then would be minus 1.65. Do you see how we get that? Here is the 0.495, 0.505, so we choose this one, minus 1.65. And that would give us a 90% confidence interval. A much smaller interval, but also a much lower confidence. So, course, next we're going to go through they'd go through some examples, how to actually do this. And here's one where they're interesting. They give you they have you do one for 98% confidence. So if you're going for a 98% confidence interval, what would alpha be? .02, 1 minus 0.98 would be 0.02, and then alpha over 2 would be 0.01. Say again? No. We're going for 0.01 would be alpha over 2. No. We calculated alpha is 0.02. So alpha over 2 is 0.01. Okay, look, if we're going for a 98% confidence level, that means we have 0.98, and alpha then equals 1 minus 0.98, which is equal to 0.02. Therefore, alpha over 2 is 0.02 divided by 2 is 0.01. If we're going for an alpha over 2, if we're going for a 98% confidence, then we're looking for alpha over 2 of 0.01. Now here we can go with, if you look on your handy dandy table E, and you find you're going to have to choose between 0.0102 and 0.0099. So again, being cautious, we choose 0.0099. You see it here? We've got to choose between these two. We choose this one, so we're minus 2.33. And that would give you the number to multiply the standard error, or the standard deviation of the distribution, or the sigma divided by the square root of n. N is what? The sample size, right? That is what gives you the that's what gives you the interval of that level of confidence. Now, in this case here, they use a large department store has found that it averages 362 customers per hour. Assume that the standard deviation is 29.6, and a random sample of 40 hours was used to determine the average. Find the 99% confidence interval of the population mean. Okay? In other words, that it averages 362 customers per hour. But it did that with a random sample of 40 hours. So, and assume, and it's saying now we're going to assume that we know the standard deviation of the whole population, the actual average number of customers per hour, all days, every day, every week. We assume that we know that number is 29.6. How or why it's, massless, frictionless police. Okay. But to use that number now, and the fact that this was based on a sample size of 40 hours, can we find the 99% confidence interval of the population? Well, the first thing we notice is, do we know if the number of customers per hour, is it a normally distributed population? We have no idea. So, but we know that the sample was taken over 40 hours, so the sample size is greater than 30. So we can do this. The best point estimate of the population mean is 362. The 99% confidence interval for the population mean is X bar, the mean, minus Z sub alpha over 2 times sigma over the square root of n is less than mu, is less than the X bar plus, okay? So let's plug in the numbers. We got 362 as our X bar. And we have, we know we're going for a 99% confidence interval. So if we use our handy dandy table E, and we look up alpha over 2 of 0.005, go actually use 0.0049 because we're being conservative, and that gives us a Z value of minus 2.58. Okay? So here we've got our 2.58 multiplying by the standard deviation of the population that we magically know, divided by the square root of the sample size, or 40. Well, that means we are subtracting, we've got 362 minus 12.1 is less than mu is less than 362 plus 12.1. What does that tell us about the confidence interval? What is our confidence interval? It's 90, no, our confidence level is 99%. Our confidence interval is plus or minus 12.1. So we have a 24.2 interval, number of customers per hour interval, that we are confident, we're 99% confident the actual average value, the actual mean of the population is somewhere between, in this case, 349.9 and 374.1, which we round to 350 is less than mu is less than 374. And that is the end of class time. So we will hit on sample size next time and then look at what happens when you don't magically know the standard standard deviation of the population.